Okay, good morning everybody, thank you for coming. Thank you for the honorary doctorate as well. It'll save me an awful lot of work coming up shortly, Brendan Walsh is my name and I'm actually doing a PhD at the moment. The topic of the PhD is an industrial water management value system framework. Just to give you a small bit of background, UCC, University College Cork, established in 1845, 20,000 students and 1,600 staff at the moment. There's a group within the college called the Intelligent Efficiency Research Group, which I'm part of, concentrate on next generation energy efficiency technologies. My own background, I'm a mechanical engineer. I worked in industry and consultancy for about 20 years before I went back into doing research. I started off in free cooling, thermal energy storage, phase change materials, and more recently went on to do, or started a PhD in industrial energy and water research. I suppose when I started doing the research into the PhD, it was focused a lot around energy. ISO 50001, the energy management standard, had only recently come out. So I was looking at that. What I found is an awful lot of people involved in that space at the time. And what I found as well was the water and energy nexus that existed, and the interaction between the two of those is of big importance really, So what I started doing was focusing more on the water energy nexus and how you can tackle energy conservation through water. One of the main users of water worldwide is industry, along with power generation, and it basically those two areas are very kind of inextricably linked. So that's the area that I decided to concentrate on. One other thing I came across as well is how water, within the water energy nexus, water is very similar to energy, and you can actually manage water as you manage energy. UCC actually demonstrated this themselves. They were awarded ISO 50001 in 2011, and they then started treating or managing water the same as they do manage energy using that ISO standard. And you can see the two graphs, the red and the green, after the calendar years after they achieved 50001. And what you can see generally, the water consumption has considerably reduced, and also the trend is basically decreasing. But it just goes to show that kind of, the similarities between the two of them. So the topic of what I kind of came to realise myself then was the true value of water. That's what I wanted to kind of focus on. A lot of the water studies that are done, water management studies that are done around the place, all around the world, there's one kind of common trend emerges from all of them, that the true value of water is never actually understood or appreciated. What I would consider to be the true value is basically all the costs that are incurred, everything from extraction, purification, treatment, disposal, etc. like that. So all those costs basically should actually be included. If you do know the true value of the water, you can manage it properly, you account for it properly, you can also use it for payback, justification for payback for any work you're actually doing. So what I decided to do was to come up with a novel framework which can be applied to achieve a true value for water. Essentially it consists of a value system and then a simulation model, and that's the basis of my PhD then. The steps involved, it's a bit small on some of the screens there. Basically, the initiation of the request is the first thing, the same as a lot of the ISO standards with a plan to check out. But anyway, the initiation of the request, the criticality there is not to underestimate the amount of work involved. And once you do start on the road, there's a lot of resources involved in actually achieving the overall system. The very first thing you do is develop a plant water flow diagram. Believe it or not, most facilities, and I'm talking kind of industrial facilities, don't have any water flow diagrams. Even the new ones, believe it or not, they have kind of essential high level ones, and then after that no one knows what happens. The water goes everywhere, and all different water streams are used, and it's all collected in different places. They don't generally know what goes on. So that's the first part, is developing water plant flow diagram. Then once you have the plant flow diagram developed, you can actually identify what your water streams are, what your water systems are, and you can categorize them. After that then, you can basically develop what I call the value-added table, where you take each of the water streams, and we'll go through each of these steps in a minute, but you take each of the water streams and then you say, right, what values have been added to that water stream to enable it to be used and disposed of. Then you determine the values for the variables in the value added, to see quantify them numerically into actual money, what each of the values are. You can then use that in a simulation model, and then once you have a simulation model up and running, you can play with it, different scenarios, and you can optimize it. What I did, I took the methodology that I developed then, and I applied it to a case study. There's a manufacturing facility in Cork who's remaining anonymous, but basically the first thing I did is develop a plant flow diagram, which is shown here. Essentially, the mains water supply comes in, there's a few branches taken off for potable water and fire water and stuff like that, and then it's held within storage tanks and then pumped around the site, used for other things like cooling water and boilers and stuff like that, and then goes into the green building there, which is the manufacturing facility. Within the manufacturing facility then, it's used predominantly to generate deionized water, which is used for cleansing baths and for cleaning the devices that are being manufactured. The water then is discharged, it goes through waste separation units and pH treatment before it's discharged again to a municipal sewer. Separate to that then there's a biological waste treatment plant as well, which takes mostly the human waste, and then that discharges as well to the sewer. So that's what the facility looks like. The types of water then you have within it they're on the left hand side there on the different rows. Typically like to be drinking water, deionized water, cooling tower water, chilled water, hot water, fire water, and so on and so forth. And then the values that are applied, or the processes, the steps that are applied to each one, then are in the columns. So basically you always start off with a mains water supply cost. Then you might have chemical treatment, processing treatment, you'd have energy consumed, you'd have a sampling or monitoring costs, you'd have system maintenance costs, you'd have the original depreciation from the construction costs being carried forward, then you'd have waste separation, waste neutralisation, biological waste treatment, and perhaps concentrated incineration disposal or else bulk disposal off-site. So they're typically the values that are applied to each of the water streams. So any row then within that table shows you all the different values that are applied to that particular water stream. What I did then was I started building up a model for the whole site, but it became very big and very complex, so I decided I'd concentrate on one system, and the system I concentrated on is the deionized water, DIW it's called. Basically it's water, purified water that's generated within the production building by a standalone skid. The deionized water then, which has the ions removed from it basically, is then used in the manufacturing process because it's relatively sanitary, and it's used in cleansing baths for cleaning the devices after they've been manufactured. The reason I picked this water stream to concentrate on is because it has a relatively high value. It's very distinct applications where it actually is used, and it's also modifiable in that the amount of water that's used in the processes can be changed, it can be influenced. If you then go back to this table that I had earlier on, and you take the row then for the deionized water, and you basically just add up all the bits that are there, and it becomes slightly more complex then because you need to take away different waste streams and how much of it goes to different directions. But that's basically kind of the simple formula then for what you end up with for how much the water is actually costing you from the time it comes in through the gate, how it's processed, how it's used, and how it's treated. This is how much per litre or per metre cube it would actually cost you. What I did then is I built a simulation model. I used Simulink, which is the graphical version of MATLAB from MathWorks, to build up a model of the whole facility, and then I zoomed in on the deionized water part of it. The reason I use Simulink, it's relatively straightforward to use. You can actually visualise the paths of all the data flow within it. You can take data off tables such as Excel, and you can export it again afterwards. You can graphically display it, you can export it, and it's easy to modify, and it's very good, I'll show you a quick snapshot of the model in a minute. Basically all the inputs I put on the left hand side, all the outputs on the right hand side, a bit like P&IDs or drawings like that. The model reads in the data, it processes it, does calculations, and then outputs it. I focused on 3 years, 2010 to 2012 inclusive, and I'm doing the readings on a monthly basis is what I'm doing for the data that's input. Typical data inputs, there's an awful lot of work goes into the actual data mining, gathering the data for all the different parts of it. That's where most of the actual physical work comes in. But to be volumetric flow rates and costs, direct and indirect costs from historical regions, from historical origins, there's a lot of work goes into that. It's very small, but that's kind of a very quick snapshot of the early site-wide plant Simulink model with all the inputs on the left hand side and the outputs on the right hand side. I zoomed in then on the deionized water and just started to see what water flows go where and what costs are assigned where and how they're apportioned. So that's just kind of a snapshot of the deionized water part, which is under development at the moment. as I said, the data, gathering the data is one of the biggest physical labour intensive parts of it. This is just from last Friday when I stopped working on it. This is just the inputs that are required for the deionized water part on its own, and the colour coding at the end is just the green is where 100% of the data got, and the yellows that is there, we've gotten rid of all the reds thanks to the God, but the yellows are where I'm going to be able to estimate them or determine them from other values. So we're using data from a lot of sources such as bills, meters, historical data, purchase orders, you're doing calculations, estimates for other bits of it, but it just gives you an idea for how many different sources of data. This is just to feed in to get a value for the deionized water and so on. That's great. What good is it when it's finished? What's it useful for? I suppose this is kind of a summary of what it's useful for. First of all, it gives you useful insight into the operation of the facility. Prior to that, people didn't know where the water went and what it was used for. Now you can see it all and you know exactly how much is going where. Obviously, the more work you put in, the more data you put in, the more information you have. You can now calculate the true cost of any water system, such as the deionized water, which is what I'm focusing on. So you can actually come up with a value for how much per litre this water is actually costing you to use. Once you have that, then that gives you data for financial justification for any modifications. One of the other speakers mentioned it earlier on that basically the cost of water is relatively small, but the true cost of the water is much higher. So if you know the true cost of the water, you can then identify the savings that are really being made, and it's much easier to generate a payback on any modifications. You can also use it for internal cost control. You know different sections of the plant, how much each section is using financially as well as volumetrically. You can use it for external benchmarking, because internal if you want, but you can also use it for external benchmarking, where different facilities around the world are doing similar processes, and how much water they're actually consuming. It's a big thing. Water usage effectiveness is another kind of life cycle assessment method, but it's an efficiency benchmark that you can compare. You can develop the water footprint for an individual product or for a factory once you have the data. You can also develop the life cycle cost for the factory or for the water, or the life cycle cost in terms of water for the actual product itself. What the model also means, you can actually do once you changes, any changes that you implement, you can see the impact in terms of the water and the energy and the cost associated with them. So in summary, what it is, it's a mechanism by which you can use your IT technology systems to assist with resources, sustainability problems through the methodology. That's it in a nutshell. Thank you very much.
Thanks, Brendan. I suspect my premature awarding of that doctrine is too far off that presentation. And thanks for giving us the commercial applications. Anybody any questions for Brendan?
Is this a model that any company will be able to take and do it, or is it something that you can do it, or are you going to have to go and do it for them?
No, ultimately it'll be generic. That's the idea. Whether I get that far, I'm not sure. You can actually apply it's probably a graphical user interface to it, and basically it asks you questions. You can plug in data, and it gives you answers. That's ultimately the plan. Whether I get that far, I'm not sure yet.
That's deeply good. One thing we realise companies don't know that.
They don't, and it's the same. I've worked in lots of different factories and chemical, pharmaceutical plants and manufacturing facilities, and they don't know. Colleges where we're doing research, they don't know. Nobody knows. But that's the whole kernel of it. Anybody else?